All right, so today we'll begin chapter 7 as we just steadily march through our textbook. And the concept we will introduce in chapter 7 is the concept of the sampling distribution. Okay. This is the last part of what I feel to be the kind of the probabilistic and theoretic side of the statistics course. So again, up through midterm 1, the theme there was describing your data. The stuff we've covered since then being probability, the normal distribution, binomial distribution, and this topic, the sampling distribution, covers kind of the theoretic side. And then, and that will be what will be covered in the second midterm, which is a week from Friday. And then the content after that will all focus on inference. Okay? So what do we mean by a sampling distribution? All right, and so the idea here is we have some population, okay? And in this case, we will think of the population, and we're taking a look at a categorical variable, okay? So maybe we have some categorical variable in the population, and this categorical variable is defined by the population proportion P, okay? Okay, so for example, imagine I've got a big, I don't know what this is, a bucket, a tub, okay, or a vat of Reese's Pieces candies, okay? All right, so Reese's Pieces candies, if you're not familiar, they're like M&Ms, except they've got peanut butter on the inside, and they come in 3 colors. There's orange, yellow, and brown, okay? Oh, here's a fun factor. Which came first, the word for the color orange or the word for the fruit orange? I don't remember. Okay, well, you can think about that. All right, so we've got orange. We're going to look at the orange pieces of candy, and so we'll say this is there's like, I don't know, 500 pounds of candy in here or something, just an extreme amount. And we can say that in this tub, P is 30%. So somehow we know that exactly 30% of these candies are orange. Okay, so this is kind of our parallel picture, and so what we are going to do for the sampling distribution is from the population we draw a piece of this, a random sample. Okay, and in the sample we have sample size n total observations, and then we'll have x quote-unquote successes, and we will have p hat, which is x over n. This is our sample proportion. Okay, so let's say I were to draw a scoop. Take a scoop out of the of candy in here. Okay, so when we look at this, when we look at the scoop, let's say I have a total of 50 pieces of candy. Okay. Now, it's a random sample, so how many pieces are orange? Maybe, let's say 18 of them are orange. Okay? So in this case, my p hat would be 18 over 50, or 0.36 orange. Okay? And the idea here is for a sampling distribution, we would go back to the population and draw another sample and do the same thing. This sample will have the same n, but this sample will produce a different p hat. Okay, so we'll have p hat 1 for sample 1. This will be sample 2. We'll have p hat 2. We got sample 3, giving me p hat 3, so on and so forth. Okay, we're going to repeatedly draw different samples. Over and over and over again, okay? And so each time, you know, with our vat of candy, we're going to do the same thing. I'm going to dump the pieces of Reese's Pieces back into the thing, stir it up, draw out another another scoop, and we'll get another p hat. Maybe another time I get p hat 28%. Maybe I get another p hat 30%. Maybe I get another p hat 22% or something like that. Okay. Conceptually, does this make sense? The experiment that we are carrying out. And so, if I do this over and over and over again, I'm going to keep track of all of the p hats I observe. Okay, so we will keep track. Keep track of all the p hats. Okay. And we will build a distribution of all the p hats. So the distribution of p hats, this is our sampling distribution, okay? So we will look shoot, this is not what I want. Okay, so we're going to look at all of the different p hats that we observe. Okay, is this okay with you all? All right, let me. I hope my internet here works. Let's see. Okay, so here I've got kind of a little applet saying exactly what we've got. Okay. So I'm going to say we got 30% orange. We're going to draw 50 pieces of candy. And we're going to just draw draw 50. So this is a simulation. Computer's going to simulate this, and it's going to spit out all the orange pieces over here. Okay. So there it goes. Do, 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 do. Okay, so here, I should be looking at the proportion. Okay, so here, out of 50 pieces of candy, only 10 of them were orange. Okay, and so the proportion of orange is 20%, and we put a dot right here at 20%. Okay. All right, well, let's do this again. We're going to draw some pieces of candy. Okay, here we got, I guess 17 pieces of orange candy. Okay, 12, 13, 14, 15, 16, 17. Each row is 6. So we have 17 pieces of orange candy, a proportion of 34%. That's orange. Okay, and I'll animate this one more time, just so we get the picture of what's going on here. Okay. Okay, and this time we got 14 pieces of orange candy, so our proportion is 14 out of 50, 28% orange. Okay, everyone's good with what's happening on the screen? Okay, so I'm going to just accelerate this. Okay, I'm going to turn off the animation, and so we see, you know, the 3 pieces that we've drawn. Okay, we got another one, 10 pieces, and then we're just putting dots, 0.26. 0.28, okay, and we're going to just build up our histogram kind of like this, okay? So after 10 samples, we've got 10 dots on our, I'm sorry, this is a dot plot, 10 dots on our dot plot, and we can do kind of 10 at a time. Let's see. So here's another 10 dots. This is 20 dots in our dot plot, okay? And so here we go. We're building this up, so now we have 80 dots in our dot plot. There's 90. This is after 100 samples, okay? And so after doing 100 repetitions of this, we're already starting to see some kind of pattern. We see that the proportion, sample proportion of around 30%, you know, 28, 30, 32, these are kind of the most common values. Sometimes we get values like 20% or 18%, even 16%, and we've gotten values as high as 46%. These happen, but not quite as often, okay? And so I'm going to just try, you know, I'm going to add another 100 dots here, okay? And we see that kind of pattern holding. Every now and then, so this one only had 12% orange, which means that there were only 6 orange pieces out of a random sample of 50. It doesn't happen very often, but it could happen. And we do see that proportions of about 28, 30, and 32%, these kind of 3 middle bars right here, are still the most common, okay? And so let's just keep building this up. So at a certain point, the dots get so close together that they just merge into bars, okay? And this is after 1,000 samples. Let's just crank this up, and we'll do like 2,000 samples. Let's see. So after 5,000 samples, this is after. Okay. So what does this kind of look like at this point? It looks kind of like the normal distribution, right? And then. And we even have the option to overlay the normal distribution on top of it, okay? Now, it's not exactly the normal because the normal is continuous, and what we see here is not continuous. Why isn't our thing continuous? Yeah. Well, that's also going to be the case with our normal the normal distribution technically goes to negative infinity and positive infinity, but that's not the answer I'm looking for. That is true that we can't go below 0 and 100. That's not really an issue in our picture here. I'm asking, why are we getting bars rather than a smooth curve? Yeah.
Because of the number of candies we
Right. If we think about the sample proportion that we have, it depends on the number of candies. So when I scoop out candies, I'm either going to have 15 orange pieces of candy or 16 orange pieces of candy. I'm not going to get 15.2 orange pieces of candy or 15.7 orange pieces of candy. It's going to be a whole number of candies, and so when I turn that into a proportion, 15 divided by 50 is 30%, 16 divided by 50 is 32%, and it's impossible for me to get values like 31% or 31.5% if I have a sample of 50. Now, if you have a different sample, you're going to get different values, but it's still going to form bars. But we will say that, hey, look, this thing looks very much like the normal distribution, and we're going to try to approximate this, even though it's a discrete distribution with bars, we're going to say, hey, maybe we can approximate it with the normal distribution. Is that okay? All right, and so let me get my little snipping tool. I guess I'll copy this. I'll put the URL in the notes as well in case any of you are inclined to try this out yourself. Okay. Okay. So this is okay. So here we have. Simulated creation of a sampling distribution. Okay. And we see the actual distribution of p hat, is discrete. Okay, but it can be approximated with the normal distribution. Okay. And over here, I have the option of displaying it as the number of orange or the proportion of orange. Okay. If I did number of orange and proportion of orange, nothing really changes except the numbers on the axis. Okay. And what's how is it going from if we look at this number, it says like 0.3. I don't know if you guys can see that, but it says 30% right here. And if I do number of orange, it says 15. Okay? So, how are we going from number of orange to proportion orange? All we're doing is we are just taking the number of orange, dividing it by sample size to get the proportion of orange. Okay? Whoops, that's not what I wanted. Okay. So, is this okay with you guys? All right. And I could, change these numbers to different things, and we could do the same thing, and it'll produce the same results. Okay. We're going to get something that looks very much like the normal distribution. Okay. Now, if we think about this, okay, here we were talking about the proportion of orange candies. Okay. But if we were dealing with the number of orange candies, what is this distribution? If I had to calculate these probabilities, and I was talking about the number of orange candies, this would actually be a binomial distribution, right? Because if we think about it, right? I've got the giant tub of Reese's Pieces. Okay? And in the tub, I said 30% are orange, okay? And I'm taking a scoop of 50 candies, n equal to 50, okay? And really I'm asking how many orange pieces do I end up with? This distribution, if I said, what is the probability I end up with 15 orange pieces? If I had asked that, what is the probability I get 15 orange pieces? Do we recognize that this is a binomial problem? This is a binomial problem with n equal to 50, p equal to 0.3, and x equal to 15. I don't know, do we see that? Kind of? Okay. And so when we ask, what is the distribution of orange pieces? Well, it's going to follow the binomial distribution. All right. Do we remember what the mean and standard deviation would be? Binomial distribution where the mean is equal to, what is it, n times p, right? 50 times 0.3, where the mean number of orange pieces is 15, and the standard deviation would be the square root of n times p times 1 minus p. .24. Okay. Is this okay? All right. Oftentimes, though, when we're talking about sampling distributions, we like to deal with the sample proportion rather than the actual count, okay? So, but for sampling distributions, we like sample proportions rather than counts. Okay. So what is the step to go from a count to a sample proportion? So if I have 15 pieces that are orange and I want to turn that into proportion, what do I do? I divide by n, right? I just divide by my sample size, okay? So in this case, we're going to have the same thing here, okay? In the population, we've got p equal to 0.3, n is equal to 50, okay? So if we were dealing with counts, for counts, our mean is equal to n times p, and our standard deviation is equal to the square root of n times p times 1 minus p, okay? In order to turn these into for proportions, all I would do is I would take each of these things and divide by p. Okay, so the mean proportion is going to be my mean count divided by n. So it's going to be n times p divided by n, and that just gives me p. So my mean proportion is just p. Okay? The standard deviation of the proportions is going to be the square root of n times p times 1 minus p, this thing, divided by n, and that just turns into the square root of p times 1 minus p over n. Okay, so these are kind of the things that we end up with. Okay, we get p, and we get p times 1 minus p over n. All right, so to put this all together, what we're saying is that, you know, if I draw a random sample of n pieces, okay, then the sample proportion p hat follows an approximately normal distribution. With mean equal to p and standard deviation equal to the square root of p times 1 minus p divided by n. Okay, so we're saying if the population, you know, so the population has proportion p equal to 30%, then our answer, okay, whenever we take a random sample, the sample proportion p hat is going to be random from one sample to another, right? Some samples will have proportion 32. Some samples will have proportion 36, okay? P hat has an approximately normal distribution. Where the center is around 0.3, but because of random chance, we can get higher, we can get lower, and the standard deviation is going to be 0.3 times 1 minus 0.3, which is 0.7, divided by 50. So that's going to be the square root of 0.3 times 0.7 divided by 50, and I get 0.0648. Does this kind of make sense? I hope. All right, so let's try to apply this, and we'll make our first clicker question of the day. Okay? Okay, so we'll say the population of Reese's Pieces is 30% orange. Okay? You draw a random sample of 50 pieces. Okay, so far everything is what we have seen here, okay? And then so knowing that the sampling distribution follows a normal distribution, okay, so about what percent, or if you draw a random sample, okay, what is the probability your sample is 36% orange or more? Okay? And these are just going to be approximate answers, but oh, and I've forgotten my normal table. Let me need to reference my own normal table. Where is this? Okay. Shoot. Okay, so I've turned on the clicker. Go ahead and try this out. Are we able to get our... Okay, we'll say, I don't know, 10 more seconds. Okay, I'm gonna hit stop here. So if you haven't clicked a button, click a button. Okay, let's see. That is the correct answer. Okay, let's go through this. Some of you guys, well, many of you guys got the correct answer. Maybe some of you aren't sure why you got that correct answer. So the idea here again is we've got a sampling distribution, right? So we want to know what is the probability that your sample has a proportion p hat equal to 0.36 or higher. That's what we want to know. Okay. So what we know is that p hat, the distribution of p hat, is approximately normal. Okay. And whenever I draw random samples of p hat, what would the mean of all of these p hats be? It should be the population proportion, which is 30%. Okay. So the center of p hat will have a mean of 0.3. The mean is equal to p, which is 0.3. Okay? And then the standard deviation is going to be what? P times 1 minus p over n, and we found this to be 0.0648 something something, 07 I think. Okay? So far my picture, whenever I draw a p hat, it should be centered at 0.3, and we want to know, well, what's the probability that we end up getting 0.36 or higher? Okay? So this is going to be an approximate answer because it's only approximately normal. It's not going to be exactly this, okay? But whenever we have a problem like this, what's our first step going to be? We find the z-score. So we're going to do z is equal to 0.36 minus 0.3 divided by 0.064807 or something like that, okay? And when I did that, I got a z equal to 0.93 after rounding, okay? Is that what we got? Okay, so I would look this up. Z is equal to 0.93, and the value I get is 0.8238. 0.8238. And that's always going to be the area to the left. Okay, so the area to the left is 0.8238. Okay, but here we're asking 0.36 or higher, so we want this side, the area to the right, so we subtract off 0.8238 from 1. Okay, conversely, I could have looked up negative 0.93, and I would have gotten 0.1762. So there is our answer there. Is that okay? All right, let's try another one of these problems. And this will probably be it for the time that we have today. Okay, so, it doesn't have to be pieces of candy. It could be something like, all right, so we'll say in the population, let's say 14% of people are left-handed. Okay, let's say a large class has 150 students. Okay, and we're going to ask So, assuming the normal distribution holds, what is the probability that this class is has less than 12% left-handed students? Okay, I got to figure out some answer choices to give you guys. So give me a second here. Okay, go ahead and try this out. Man, some of you guys are on top of it. Okay, so while you guys are working, I'll tell you about the color orange versus the fruit orange. So in Old English, the color that we call orange today used to just be called yellow-red. Or was it red-yellow? They called it red-yellow or yellow-red, something like that. It was just a mishmash of words. But then the fruit oranges appeared in Spain, and they were called naranjas. But then, and as they made their way into the English language, we borrowed the name for the fruit, naran. But just they kind of butchered it from naranja to orange. So so if you look at the spelling of the fruit naranja, it kind of looks like orange, as if somebody just really butchered the word there. But anyway, the more you know. Okay, we're gonna run out of time, so I'll give you guys another, I don't know how much time I can give you guys. Wait, okay. This is high stress situations and with the clickers. Okay, I'm gonna go ahead and start doing the answer while you guys still work. Again, we are saying the distribution of p hat is approximately normal. And if the population is 14%, we would expect the center of our distribution to be 14%, okay? We can say that it's approximately normal where the mean is 0.14 and the standard deviation is the square root of p times 1 minus p over n. So our standard deviation is going to be 0.14 times 1 minus 0.14 divided by our sample size 150, and if I did the math here correctly, I got our standard deviation to be 0.02833. And we are asking, what is the proportion of getting 12% or less? So I'm going to go ahead and hit stop on the timer here. And so our answer would take turning the 12% into a z-score. Okay, and if I did this correctly, I would get negative 0.02 divided by 0.02833. I get something like negative 0.71. Okay, and so as I look this up in the z table, negative 0.71, and I think I did this correctly, is 0.2839. So the area over here is 0.2389. There is our answer there. Okay, that's it for today.